Banks play a crucial role in the market economies. They decide who can get finance on what terms and can make or break investment decisions. For markets and society, individuals and companies need access to credits. Banks use credit to decide whether to sanction a loan to the individuals. The goal of this project is to build a model by predicting the probability that somebody will experience financial distress in the next 2 years, which helps banks determine whether or not a loan should be granted. In the next few parts, we are going to explain how we process the data and to build this model.
Hi, this is Divya Kapoor. Thank you, Ranran, for sharing the details about the project and the data used for the same. As we have gathered the data, I will now talk about the data pre-processing and the variable selection. So the first step that we have done is we have done revolving utilization of unsecured lines, which is also known as balance to limit ratio. It is expressed as a percentage of total balance on a consumer's credit cards to the total credit limits of the cards. It is a very important component when calculating credit scores, and it comes second only to payment history as an indicator of credit risk. When the percentage is closer to 100, it means the consumer is maxing out its credit limits and it's being trapped in debts due to high interest that's charged by these credit cards. The value of revolving utilization of unsecured lines mostly exists between 0 and 1. However, it can exceed 100% as well in few cases when the balance exists on credit cards when the accounts are closed. Hence, appropriate imputation is required. In this case, value exceeding 5 is only about 0.17 of the whole data, 0.17% of the whole data. So it's reasonable to assume that these values represent consumers whose credit cards were closed, and we have decided to apply coded value -1 to these outliers. The next variable we talk about is age of the borrowers in years. Initial observation for this is the original values, they follow an approximate normal distribution or Poisson distribution, and variable doesn't appear to need any further data cleaning. There's only one observation, which is 0, and we have omitted this. This slide is about the number of times borrower has been 30 to 59 days past due, but no worse in the last 2 years. Initial observation is that the original value contains some coded values such as 96 and 98, where 96 is others and 98 represents refuse to say. So these values need to be imputed so that their large quantitative values do not skew the entire data set. For the data cleaning, since both of these values have their own meanings, so it's inappropriate to treat them as outliers and directly omit them. So we decided to change them to coded value -1, and we have applied the same approach to the variables number of times 60 to 89 days past due, not worse, and number of times 90 days late. They contain the same set of coded values. So here we'll talk about the debt ratio. Debt ratio is a financial ratio and it measures the extent of anyone's leverage. If it exceeds 100, then it indicates that there are more debts than the assets or income. The debt ratio is defined as the ratio of total long-term and short-term debts to total assets. Can be expressed as a decimal or percentage. It helps to determine the risk-taking capability of a borrower on an organization. So initial observation for this particular variable says that it's quite abnormal when monthly income is missing or when monthly income is 0. So for data cleaning, when monthly income is missing, we have substituted the denominator by 1, and when monthly income is 0, the value of debt ratio should also equal to the value of total debts, since 0 cannot be a denominator. However, the former imputation is no longer available when monthly income is not missing this time, so we decided to apply coded value -1 to the new debt ratio for this. So here we'll discuss the monthly income. The initial observation about this variable is that around 0.2% of the total observations are over 50,000, which indicates the variable seems to have some outliers at the top end. There are also large amounts of missing values in this variable which are to be imputed. For data cleaning, we have seen since the frequency of outliers is very low, we can directly remove them. And when monthly income is missing, the value of debt ratio is actually the value of total debts. So we decided to apply the formula monthly income is equal to total debts median into debt ratio to reverse engineer the monthly payments variable when they are not available. This slide is about number of open loans like installments for car loan or any other mortgage and lines of credit like credit cards. So initial observation about the variable is that the values seem fairly well distributed with a very few outliers. And for data cleaning, we have taken all the observations above the 99th percentile as outliers and have been drawn. So now we'll talk about the number of mortgage and real estate loans included home equity lines of credit. So initial observation is same like the last variable. The values are fairly well distributed with a few outliers. And we have done the similar data cleaning here as well, taken all the observations above the 99th percentile as outliers and have been dropped. So here we will talk about the number of dependents in the family, excluding themselves, like spouse, children, etc. Initial observation is around 2.6% of missing values are there, and there are some outliers that need to be dropped to improve the chart. For data cleaning, since there are only few missing values, median of dependent is applied to replace the missing data. And observations above the 99th percentile were taken as outliers and dropped. This slide shows a table which has been created by the results which are obtained after the data cleaning of all the variables. So now we are done with the data cleaning of the variables we are using. Now we have to select few significant variables for our models. Here we have plotted the Pearson correlation coefficients in the table, and as you can see that there is no obvious correlation between any of these different variables, and the highest correlation coefficient is 0.73, which is between the real estate and total debts. And if we plot the same, we can see some pattern between these two variables. However, there is no obvious linear correlation between them. So we have used stepwise variable selection method. Both forward and backward selection is done. For the raw data, the variable unsecure and data debt ratio are removed. Then we have removed all the outliers and kept the missing values. Then again we have applied stepwise and found all the variables which are significant except debt ratio. Again, stepwise variable selection method is applied, and we have used median to replace all the missing values for both income and dependence. And in this case, if we compare the summary in the last slide, the p-value of debt ratio became significant here. Also in this table we have changed the debt ratio to total debts. The coefficient has changed from negative to positive. That means income is negatively related to the response variable. So from the results above, after data imputation and data cleaning, all the features are significant to the response value. Hence, it's not necessary to remove any variable. So now we have completed the data pre-processing and variable selection, and now our another team member will talk about the model selection. Thank you.
Next, we will talk about the model selection. Let's take a look first at the stepwise GLM. So we can see from the figure that we apply all the variables. The AUC value now is only about 0.686. Next, we remove all the outliers and keep the missing value. The AUC value
it becomes 0.848. So compared to AUC, which is only 0.695 for raw data, remove the outliers helps improve the result a lot. Next, we removed all the missing values. Reapplying the model again, the result of AUC value is reduced a little bit, and the variable selection doesn't change at all. The AUC for stepwise GLM is 0.836. The AUC value is reduced slightly, and hence missing values are important for the model. Then we replaced the debt ratio with debt. The AUC value becomes 0.8535409. In this case, AUC value is the highest, so this is the best model for the stepwise GLM so far. Now let's move to our second model, L1 penalized GLM. We first keep the missing value, apply the model, the L1 penalized GLM, and use 10 cross validations. We find that the lambda equals 0.00484244. There has minimum cross-validation error and still no variable removed. The AUC value is 0.858967. It is better, a little better than stepwise GLM. If we replace the debt ratio with debt, as same as what we did to our model 1, we can find that the ACU value becomes 0.8539091, which is a little bit higher than the last form of penalized GLM. This slide is a small summary of our comparison between stepwise and L1 penalized GLM. If we take a look at this data, we can see that generally L1 penalized have slightly better answers no matter which category they fall in. And if we use the debt to replace the debt ratio, we can even have a best AUC value for the L1 penalized GLM model, which is 0.8539091. Our third model is random forest. By using this method, we use 9698 as coded value minus 1 of variable time 30.59 times 60.89 times 90. We apply two methods of approaches. One is regression, the other one is classification. We find that the AUC value is similar to the other two methods, which is when it is under regression approach, the AUC is 0.8522. When we use classification approach, the AUC is 0.8528. So the conclusion is that the results of three methods and different ways of data cleaning and transformation for the GLM and random forest doesn't have significant differences on AUC value. In contrast, the data imputation have more effects on the increase of the AUC value. Because random forest can handle the coded value, will not affect by the interaction between variables, and can reduce the overfitting, the random forest method will be the best option for this data.